Hello everyone, hope you're doing well and safe, and thank you for joining us in AWS Workshop from Home series from AWS Educate. I'm super excited to be here as we're going to share with all of you all you need to know about AWS DeepRacer. That means we're going to cover from how to get started and build your first reinforcement learning model with AWS DeepRacer. So by the end of this session, what we really hope is for you to have some understanding of what reinforcement learning is and how easy it is to get started with reinforcement learning to start and train your own DeepRacer model so you can take part in one of our DeepRacer League or going out and creating your own community race. Just to give a bit of introduction to today's speakers, my name is Donnie Prakoso, Senior Developer Advocate at AWS, and will be joined by Suresh from AWS Educate. Our mission today is to guide you on how you can get started with AWS DeepRacer, starting from its theory to implementation. So if you have any questions, feel free to post it in the provided question box and we'll answer it at the end of the session. I'm also happy to announce that AWS DeepRacer Women's League ASEAN 2020 is now open. This is really a good opportunity for those who want to participate by submitting their models, and this is to empower more diversity and inclusion in our community. So don't hesitate to join us, and you can find more information by visiting the link on the screen. This is how we structure our session for today. We will start with talking about the origin of DeepRacer and few components that you need to know. Then we'll shift our discussion to reinforcement learning. We will cover an overview of reinforcement learning, what it is, a few terms that we will use, and how reinforcement learning works in DeepRacer. We will also guide you to build your first reinforcement learning model for DeepRacer with our step-by-step console walkthrough. And after you have your model, you're ready to participate at AWS DeepRacer League. For those who are not familiar with DeepRacer, don't worry. Let's watch the following video to get an idea of what DeepRacer is all about.
Welcome to the AWS DeepRacer League 2020 presented by Accenture. These are 1/18th scale RC cars that are fully autonomous thanks to reinforcement learning.
With new sensors that enable it to detect objects. We are swapping out single camera and putting in a stereo camera and light detection and ranging sensor, or known as LiDAR sensor. Now these sensors unlock new possibilities, resulting in the new race formats that we introduced last year at BrainFan 2019. They are head-to-head racing and object avoidance in addition of time trial. Second component is a 3D racing simulator that you can find in the AWS DeepRacer console. Now you don't have to wait for your physical DeepRacer to start learning. You can start right now in the AWS DeepRacer console. The 3D simulator in the AWS console is where the building takes place. And it's really your starting point to build your machine learning skills for building machine learning models. And once that you have that kind of confidence, you can then showcased during any race competition by submitting your models, which is a good segue for the next component, which is AWS DeepRacer League presented by Accenture. You can build models to get ready for racing in the 2020 AWS DeepRacer League either in person or virtually. And you can also build models to race against friends and colleagues using the new community race feature. So that's all the components in AWS DeepRacer, and I just want to reiterate that you can start learning right now by logging into AWS DeepRacer console. We need to lay a foundation first before we can start building our model. So with that, let's cover the basics of reinforcement learning. Let's see how reinforcement learning fits in the AI context. Artificial intelligence seeks to create machines that seem to have human intelligence, and this is the general concept. One aspect that humans are good at is learning how to classify things or events, and also make simple predictions based on past behavior. Machine learning is a subset of artificial intelligence that aims to replicate this human ability. Machine learning uses statistical techniques to build models that are good at making predictions. And these statistical techniques learn from data to figure out what the patterns are that ultimately leads to the prediction. Machine learning has three main categories. With supervised learning, we can build a model to predict a value or to classify data. Models are trained up using large amounts of curated training data with labels. With unsupervised learning, things are a bit different. Models are trained to identify similarities in large amounts of data to aid classification. Now, training data doesn't have explicit labels in unsupervised learning. And with reinforcement learning, we finally can build the model to autonomously predict which decisions to make in a specific environment. Now, the models are trained in a simulated environment where the models can interact with the environment and learn based on the outcome of action if an action was good or was it bad. And that was a quick overview for three main categories in machine learning. So let's get into a concrete example to illustrate how reinforcement learning works. Essentially, reinforcement learning is built on an idea. For example, when was the last time you used a reward to incentivize the right behavior of your pet? Think about our approach used to train our pet. We give cookies for good behavior and no cookies for bad behavior. Now, during this training, we give an instruction to our pet with a simple action like sit, or stay, or roll, or even more complicated action. The goal of this game, of course, is for your pet to do all kinds of tricks. From training our pet as an example, let's dive deeper into reinforcement learning by understanding few terminologies. To be more detailed, reinforcement learning is a machine learning technique that enables an agent to learn in an interactive real-time environment by trial and error using feedback in the form of rewards from its own actions. Within the simulator, we have an agent that acts autonomously in a given environment to reach a specific goal. So, what is our agent? The agent is the AWS DeepRacer vehicle. And what is the goal of the agent? The goal is to finish a lap around the track. The environment is the surrounding area for our agent interacts. In this case, the environment is the track we designed with AWS RoboMaker. The state is defined by the current position within the environment. Basically, this is what the agent can see through its camera. The action can be defined with how fast or how slow the agent decides to run, and it will be also including the direction. And for every state, our agent needs to take an action to try and achieve its goal of making a lap. And depending on which action it takes, it will be given a reward. If the chosen action gets the agent closer to the goal, you can reinforce this action in the future through a positive reward, or otherwise discourage it with either a negative reward or no reward at all. And this reward is provided by the environment itself and specified through a reward function. A reward function is code written to incentivize behavior through parameters defined by the creator of the environment. And the last concept here is an episode. which represents each iteration where an agent goes from the start position to a termination state. A termination state means if it drives off the track or finishes a lap around the track. So those are the terms that we need to know so we can fully understand the whole concept of reinforcement learning in AWS DeepRacer. Okay, so we get it now. We have an agent which interacts by doing some actions within the environment, and it will be rewarded depending on how close or far from the goal. So what is the most crucial component to help us crafting reward? And yes, it's reward function. The reward function incentivizes particular behavior and is at the core of reinforcement learning. To run your AWS DeepRacer car, providing a reward function will be your most important job. Let's look at this race grid to see a practical example of a reward function. Each square is a state and the green square is the starting position, while the finish line is the goal or terminal state. We design the squares at the edge of the track as terminal state, which will tell the vehicle that it has gone off the track and failed. Now again, a reward function is a function to help your agent to determine if the action it just took was good or bad based on the outcome of the action. Now the reward function is a logic that looks at the next state the agent is in and based on that assigns a reward. The reward function can be seen as the logic that will incentivize the driving behavior you want your agent to learn. So looking at this race grid, the next question is, how will you incentivize the agent to drive on the yellow center line? By assigning a higher reward to the center line, our model will learn that actions that drive on the center line gets higher rewards than action that leads to the sides. Initially, our agent won't have any idea of that value of landing in a state or the reward associated with an action. So our agent first needs to explore the environment and then explore some more in an iterative fashion to build up this knowledge. Our model starts off not knowing anything about the reward for specific actions, and then repeatedly explores the grid until it moves out of the track or reach the destination before it starts again. Our model is learning through iteration. As it drives around, the vehicle accumulates reward from the scores we have defined. Besides recording each step, it is also learning what rewards the various actions from a specific state leads to. Now, all steps from start to going off track or the finish line is called an episode. To get the best model, the agent first needs to explore the grid to ensure it covers large rewards that can drastically change driving behavior. Now, this is normal, and we call it exploration. First, the agent needs to explore to see what rewards can be obtained from various actions tried in the various states. It won't settle for the first best thing. It will first explore. As the agent gains more and more experience through the exploration and iteration, it starts learning where it repeatedly gets higher rewards. It then starts exploring less and moving on to exploring what it has learned. Now, convergence happens when a model starts repeatedly picking specific actions depending on the state it is in. Now, the model is optimizing for expected cumulative return, and model performance will be the same repeatedly, with subsequent updates to the model not really changing the model behavior. However, there is a trade-off between exploration and exploitation, which you need to configure with a hyperparameter. If you explore too much, your model may take a very long time to converge. If you exploit too soon, your model may not find the best driving behavior and potentially also fail to converge. Now let's go back to the previous grid. What we have here is a small grid, and our agent can easily go to each square and test all actions to determine which action will result in the highest expected cumulative reward, assuming that in each subsequent square it will choose the action with the highest expected cumulative return. This mapping, where we know the value of being in a square, is called a value function. Once we know the value of a state, we simply choose the action that takes us to the highest value. If you can map a state directly to an action, then you have a policy function, and the model is sometimes called a policy network. This idea of knowing how valuable it is to be in a state is a very important concept. The value of being in a state can be seen as the expected cumulative reward that can be achieved from that state onwards if the agent keeps following the optimal policy. So let's recap what we have discussed about reinforcement learning in AWS DeepRacer. Reinforcement learning being a form of machine learning where we are interested in creating a model that can learn how to make autonomous decisions in an environment based on the reward that it receives when it interacts with the environment. Reinforcement learning in the real world is like training your pet to behave using cookies or rewards. The reward function is the logic that incentivizes our model to learn the driving behavior we want the model to do. In a grid world, our agent first explores the environment to learn what rewards can be achieved from its state based on the various actions. And the reward function is the logic that assigns a reward based on the outcome of each action. It uses these interactions to build a map of the value of being in each state. Now, the value of being in each state is the expected cumulative reward that can be achieved from that state onwards when following the optimal policy. But how does the DeepRacer agent learn? In DeepRacer, our agent is the car, and it interacts with the simulated racetrack environment during training. In the simulator, AWS DeepRacer drives around the track, taking pictures about 15 frames per second. That picture is our state. For each picture, DeepRacer will take an action and end up in a new state. And this is called a step. DeepRacer Evo has stereo cameras and LiDAR, so it has more in-depth view of its state and can sense objects too. DeepRacer will collect experience, the state, action, reward, next state tuples, and all steps from the starting point until it reaches terminal state is called an episode. Once the agent has collected experience, which you need to specify in hyperparameters, it starts updating and training its model. The goal during training is to figure out which action in which state will lead to the maximum cumulative expected rewards. So once the model is trained, it is sent back to the agent to collect more experience. And as for the exploration and exploitation, once again is controlled through the model hyperparameters. However, unlike the grid race, DeepRacer cannot explore all states in the simulator. It will simply take too long, if not impossible. So we cannot fully determine the value of ending up in each state. Now the next question would be, how do we select the action if we don't know the value of the states? The answer is approximation. This is commonly referred to as policy optimization, which means we optimize the policy function mapping state to action in order to achieve our goal. Let's look at the common method of doing policy approximation using a method called vanilla gradient ascent. Vanilla policy gradient is an example of policy optimization, and this is a method where we parameterize our policy function. The parameters are simply the weight in a neural network, and the neural network represents our policy function. Essentially, this policy function takes an image as input and maps the output as action. We then optimize that policy to get the best action from each state. And our goal is to get the maximum cumulative reward. We train our model, updating the weights by trying to maximize the cumulative future reward, and in doing so, we give higher probability to the action that leads to the higher cumulative future reward. DeepRacer uses a form of policy optimization called proximal policy optimization. Hyperparameter is a key concept in machine learning, and this also applies in AWS DeepRacer. A hyperparameter is a configuration that is external to the model and whose value cannot be estimated from data. Understanding hyperparameters is a key to tune your model performance as they have a direct control behavior to the training algorithm. Different algorithm has different hyperparameters, and in this section, we'll cover hyperparameters used in AWS DeepRacer. The first is gradient descent batch size. AWS DeepRacer has an experience buffer which consists of a number of other data points collected over a fixed number of episodes of varying lengths during training. And gradient descent batch size represents the number recent vehicle experience sampled at random from an experience buffer and used for updating the underlying deep learning neural network weights. Why random sampling? Because it helps to reduce correlation in the input data. Moving on to number of epochs. Number of epochs represents how many passes through training data to update the neural network weights during the gradient descent. Next, learning rate. Learning rate controls how much a gradient descent or ascent update contributes to the network weights. Next, entropy. We've talked about exploration and exploitation. And entropy is the degree of uncertainty used to determine when to add randomness to the policy distribution. Moving on to discount factor. Discount factor specifies how much of the future rewards contribute to the expected rewards. Lastly, loss type. Loss type is a type of the objective function used to update the network weights. Now, these parameters correlate one to each other and could help you to achieve your objective. For example, if you want to have a robust model, you will need to tune your gradient descent batch size, number of epochs, learning rate, and entropy. Now, learning all of these hyperparameters could be daunting if you're trying to understand them all at once. So our suggestion is to take it slow, learn one thing at a time, and we encourage you to do trial and error. Here is the neural network architecture that we use in AWS DeepRacer. The first layer is an input layer. This is followed by a 3-layer CNN to help identify the features from our images needed to make driving decisions. Finally, we have 2 fully connected layers to help determine what action we should make. Think of this neural network as a mathematical formula. Each node in the network determines how much weight should be placed on certain features in the image. And when the weights for a certain action all become big enough, the output of the network will indicate a higher probability for the specific action. Now, during training, these weights are adjusted. Weights are adjusted so the car maximizes the expected cumulative return during racing. AWS DeepRacer is built on top of various AWS services. Amazon SageMaker trains the model. AWS RoboMaker provides the simulation environment. Amazon S3 stores models. Amazon CloudWatch stores logs, and Amazon Kinesis Video Stream displays the video in the console. So when you start training a model in AWS DeepRacer, this is what happens in the background. AWS DeepRacer starts an Amazon SageMaker and AWS RoboMaker container in your service account and links these two. It then passes the right parameters to start the training. The experience tuples, which is state, action, new state, reward, are generated in AWS RoboMaker. After a specified amount of experience which is defined by the hyperparameters is obtained, it is sent back to Amazon SageMaker to train the model. The new model is then sent back to AWS RoboMaker to get more experience, and the process continues. The output models, videos, and metrics are stored in other AWS services such as Amazon S3, Amazon CloudWatch, and Amazon Kinesis Video Streams. Now, once that you have your model ready, you can download and plug into your DeepRacer device. DeepRacer is powered by Intel OpenVINO to enable model optimization for fast inference on the edge. So these are the technical specs on what's going on under the hood of AWS DeepRacer Evo. It runs on Intel Atom processor with 4 GB memory. It has built-in Wi-Fi, which we need to connect during physical events to control the car. It also has 4-megapixel camera with 360-degree and 12 meters scanning radius LiDAR sensor. The application inside runs on top of Ubuntu operating system with Intel OpenVINO Toolkit and ROS Kinetic. It has 4 USB Type-A ports, 1 USB-C port, 1 micro USB, and 1 HDMI. With all of these ports, it makes DeepRacer pretty much configurable for future upgrade. One of the cool things which powers DeepRacer is OpenVINO Toolkit. OpenVINO stands for Open Visual Inference and Neural Network Optimization. It's a free toolkit released by Intel to help developers and data scientists speed up AI and deep learning workloads. streamline deep learning inference and deployments, and enable easy heterogeneous execution across Intel platforms, including accelerators. The Intel distribution of OpenFINO Toolkit is embedded in DeepRacer. This means that you can easily take the reinforcement learning models that you've just trained and use the Toolkit Model Optimizer to convert and optimize your trained model. In DeepRacer, the inference engine allows you to deploy on the Intel Atom processor. With the standalone version of the Intel distribution of OpenFINO Toolkit, the inference engine allows us to deploy across multiple Intel architectures. OpenFINO is also framework agnostic, so you can build a powerful optimizer on models trained through TensorFlow, MXNet, or PyTorch, and then use the inference engine for high-performance inferencing. Okay, so we have covered most of the things that you need to know about AWS DeepRacer. And let's go through the console to help you get started for building your first model. Our aspiring colleague Suresh from AWS Educate will guide you through AWS DeepRacer console and all important things that you need to know. Suresh, over to you.
Thank you, Donnie. Hey everyone, I am just about to share how we get into using AWS DeepRacer. So this is going to be a live demo, as Donnie was saying. So let's walk through that right now. Now, as you can see on the screen, this is the AWS console. Now you can get to AWS DeepRacer pretty much via the console, right? You can find a service by simply typing AWS DeepRacer, and you'll see that appearing up here. Right, so let's go ahead and click on that. Okay, now the other thing I should mention is AWS DeepRacer is only available in North Virginia. So if you are in another region, so remember to switch it to US East 1 before you start using AWS DeepRacer. Okay. Now let's go get on with getting started with this. So under reinforcement learning, you see the option called Get Started. So go ahead and click on that. Now, what we're going to do is we're going to create an account. Now, normally this takes 5 minutes, but we won't be going through the full 5 minutes for creation of resources, right? So we'll be going through some other stuff, and then we'll come back to revisit this. And I've also got some, templates set up so that I can kind of show you what the finished state looks like as well. Okay, so let's go ahead with this. I'm going to go ahead and click on Create Resources now. Okay, now while that's going on, let's start looking at a few different things. One new interesting feature that we have on AWS DeepRacer is the garage. So let's go to the garage itself. Now, the garage now allows you to build your own personalized DeepRacer vehicle on a virtual format, right? So we've got the original DeepRacer here, which is it just comes with a camera, a 3-layer CNN, and then a speed limit of 1, and then steering angle of 30 degrees. But you can create your own. And how does that work? Right. So let's go ahead and try one now. So I'm going to build a new vehicle. Right. So when I click on building new vehicle, I've got two options. I can go for a camera, which is basically single lens 120-degree field, or I can go for a stereo camera, which is composed of 2 single lens cameras. Right, and the benefits are actually mentioned here. Now, just for this example, I'm going to say camera is good enough. I don't really need a stereo camera. Now, there are a lot of reasons why people pick stereo camera, though, is if you're taking part in a competition that involves avoiding obstacles and all that. So you need more cameras to probably figure out where your obstacles are and all of that. All right. So that's probably why you need stereo camera. But if you're just going for a straightforward time trial, typically a camera should be sufficient. You don't really need a stereo camera. Likewise, add-on sensors, again, I think this would be particularly useful if you're taking part in a head-to-head race. But again, for a time trial, I think this is unnecessary, so we won't need to add on a LiDAR sensor. Now, neural network topologies, right? Obviously, a 5-layer CNN is always better, right? It's a deeper neural network, right? It will take longer to train, but you will actually be able to handle more complex tasks. Now, for a time trial, it's not really a much more complex task because you're not worried about objects on the road. It's a straightforward way of learning. It needs to figure out how to stay on track and complete the track in the fastest time possible. So I would often recommend a 3-layer CNN if you are just taking part in a time trial, right? So let's go ahead and pick a 3-layer CNN and click on next. And then we've got all these other settings, which is steering angle, the granularity in which you can steer. So whether can you go by in 7 degrees or 5 degrees or 3 degrees, right? So there's a maximum angle of 30 degrees, but within there, how much can you deviate and turn to the next angle, right? So you can actually decide aspects like this. You can set a maximum speed. You can set the speed granularity as well. So in this example, what I am going to do is I'm going to leave the default settings here, right? I'm going to say, okay, I'm happy with a maximum speed of 1. I'm going to go for a speed granularity of 2, right? Where you can tweak upwards and downwards accordingly in that fashion. And this gives you a sample of what the action this looks like, right? So if you're giving a speed granularity of 2, this is the tweaks and changes that can happen from a speed and a steering angle perspective. Right, so let's just for the sake of seeing how this differs from one and the other, let's click on 1. Now, when I click on speed granularity 1, can you see how the speed now remains the same? Right, it's just the steering angle that's actually being changed. Now let's go ahead and click on 3 as well. Now again, you can see how the speed granularity differs when you're switching degrees and angles as well within different phases, right? So I would typically go for 2. I think this is just nice to have in terms of a setting. I don't think we need 3 different speeds. So let's go ahead and click on next. And for this example, I'm just going to call my DeepRacer champ. And I'm even going to give it a color that I like. So I'm going to go for blue. And then I click on that. All right. Now with that, I've just built the vehicle, right? So we're done with the vehicle, but we're nowhere close to actually starting to build the AI model that's actually going to power the car to actually move autonomously through the tracks. All right. So let's go on to the next few steps as well. So since you're done with a new vehicle, let's see whether the resources are ready right now. Let's go back to get started again. Okay, it seems like the resources are ready. Let's go back to your models now. You can create your models in 2 ways. You can do it from your garage, or you could come back to your model area here and click create model. So I will often go for your models, and let's go ahead and click create model. Okay. Now, this is what happens in this mode, right? So it's going to give you an overview of the what happens during a reinforcement learning, which is something that Donnie was covering a while earlier. You guys listen to that. And we're going to give this model a name and then come up with environment simulation, meaning to say which track are you going to train this particular model for, all right? So let's just give this model a name. I'm just going to call this model name, workshop champion, perhaps. Let me just put that together. All right. So workshop champion. Sometimes we can actually give it a description. If you have different models, you want to just remember how you tweaked a particular model. You could actually even put in aspects here that you decided in terms of maybe your parameters or your hyperparameters. These are aspects we're going to cover later, right? So don't worry about what that means yet. Okay. Now let's choose the track now. Just for the purpose of this race, this model, I'm only going to train it for one particular track. I'm going to train it for the 2019 DeepRacer Championship Cup. All right. So let's train it for this particular track. And I'm going to go ahead and click on next. Now, again, you have the option of choosing the race type. You could train your car for object avoidance, head-to-head, as well as time trial. We are just going to train it for time trial. So that's great. Now, remember, we built a couple of cars. We had the champ, and we also have the original DeepRacer. So I am going to opt for the champ. Okay, so I'm going to choose that vehicle, and let's go ahead and click on next. Now, here is where things start getting interesting. Now, you would have heard about how reinforcement learning works from Donnie a while ago, right? So just to recap again, the way it works is it's kind of like a carrot and stick method, right? You are basically giving it information to say, if you accomplish a certain task, I'm going to give you X number of points. if you don't accomplish a certain task, if you have done something that I don't want you to do, I'm going to take points away from you. And from the car's perspective, from a reinforcement learning perspective, what does it understand? That it needs to maximize the score, right? So it needs to get as much points as possible. So we need to give it a lot of functions that will allow it to reward itself to gain the fastest possible score it could, right? Now, highest possible score that it could, right? So now let's look at some reward examples. Now there's a template here already put in place. Before that, let me just go through with you some of the parameters that are in place here. Now, there are a few parameters that you can tweak, right? So you can actually talk about parameters in relation to having every single wheel of the car on track. Do you want to take note of that, right? Do you want to take note of its X coordinates or Y coordinates? Take note of things like closest objects. This is more for head-to-head objects and stuff like that. Taking note of track length, track width, right? That means how wide the track is, and then this is how long the track is. And we can actually reward it based off steering angles. We can reward it based off speed or tweak speeds, etc. So these are all the parameters that you have, right? So think of it as like a set of options that have been given to you that you can modify, right? So that your reward system will actually work according to the way you think it should work best to complete the track in the fastest time possible, right? So let's go back to the reward function space again. Okay, so we're back in the reward function. Now, in here, right, so just to give you a basic sense of this reward function is pretty clear, okay? All it's telling you is firstly, it's measuring a sense of track width, and then it's figuring out the distance from the center, and then it's calculating this, right? So it's giving 3 different points. So it's saying that if your track, the marker point 1 is 0.1 times track width, all right, meaning to say it's within the within going a little bit within the track width, 0.25 a little bit more off, and 0.5 a little bit more off, right? So how it works, now look at the reward system now. So this is the marker, this is the track width, right? Now the highest reward is given for marker 1. Why? Because it's only 0.1 of the track width, which means it's not steering too far away from the track width. All right, so that's why you're giving it the highest reward, so it's not going off track. As it gets further away, all right, marker number 2 and marker number 3, you can see the reward keeps getting lower and lower. Now, last part, you'd see this, all right. If not, you're going to give this particular exponential reward, which is basically a negative score. All right. Now, this means that the car has either crashed or it's gone completely off track. Right. So very simple parameters. Now, in case you're not satisfied with parameters, that's where the fun part comes. That's why we've opened up a lot more parameters to you, which I shared a while ago, right? You can go through those parameters and figure out a logic that you could put in place here to increase the rewards to the car or optimize the car to the point where it's getting the maximum score. But more importantly, that maximum score must relate to the fact that it's completing the time trial in the fastest time possible. And we also got some examples to help you along. So if you click on reward function examples, right, there are a few types. For time trial, we have 3 different sample codes, which is that's the one that you just saw, which is follow the center, or you can go one which is just about staying within the 2 borders, or another one that's simply, but look, I just don't want you to go right or left, just stay a lot more steady, right? I don't want you to steer too much up to the right or to the left, right? So these are some of the example reward functions. You have code here. You can actually click use code and it'll actually replace the code. Now, I am going to do this. I'm going to switch the reward function to now be focused on stay inside the 2 borders. So let's use this code instead. All right. Okay, so now I've changed my reward system, okay, which is basically by default, I wanted to give an extremely low reward, right, for this. Okay, and then if all wheels on track is a little bit steered, if it doesn't steer too much, I'm going to give you maximum score. So that's all I'm training it to do. I'm just training it to just simply keep all wheels on track and not to get it to steer too much away from the center, right? So, and I'm going to give it a score of 1.0 at any point in time. Okay, as long as it stays very close to the center. All right, now I'm happy with this. Now let's talk about a few more different aspects as well. So let's talk about particularly what we call the hyperparameters. Okay, let's expand this. Okay, let me scroll down. Okay, let me just stop at the gradient descent batch size. All right, now let's walk through what each of these parameters mean. Okay, so where it concerns gradient descent batch size, right? This is basically the number of recent vehicle experiences sampled at random, right? Where it keeps updating rather the underlying deep learning neural network weights. So, for example, if you have like say 5,000 experiences already logged or kept, and you specify a batch size of say 512, right? And if you ignore random sampling, you will actually get 10 batches of experience. And each batch will be used to update your neural network weights during the point where it's training the model. So what that means is, if you use a larger batch size, right, to promote more stable and smooth updates to the neural networks, okay, that's going to be really good, but there is one issue though. Your training though is going to be a lot more slower. All right, so think about the trade-off here. Okay, so in this example, I'm just going to leave it at. I'm maybe going to go for something midpoint and say, look, I do want it to be, I do want the updates to the neural network to be a lot more smoother, but I don't want it to be taking up, too much time in terms of training. I want it to be a little bit more faster. So I'm going to go for 128. Okay. Now, number of epochs, right? So let me explain what this means, right? So an epoch represents like a single pass through all batches, meaning to say something like this. Okay, how do I put this? Okay, something like this, right? So let's say you put in something like 10 epochs, like what you see here, right? So it implies that you will actually update the neural network weights using all batches one at a time, but you will repeat this process 10 times. Okay, so again, what does that mean? If you are using a larger number of epochs, right, because you want more stable updates, it means your training time then slows down visibly as well, right? And to look at this against the batch size, right? So typically, if you have a very small batch size, you can actually use a smaller number of epochs as well, right? So you don't really need something that's repeating this process 10 times. If you have like the batches or experiences are a lot more smaller, right? For instance, so in this case, I just brought it from 64 to 128, but I think I'm happy with the epochs being as high as it is right now. But maybe, just maybe, I might just bring it down one notch and say, you know what, maybe I don't need this to be that high. I want to train this a lot faster. I'm going to go for 5. Okay. And then we've also got the learning rate. Now, learning rate basically controls how big the updates to the neural network weights are. Now, this simply means that you need to actually change the weight of your policy to get the maximum cumulative reward, right? Now, a larger learning rate will lead to faster training, okay? But it may struggle to actually converge. Likewise, a smaller learning rate leads to stable convergence, but can take a long time to train. All right. So again, you need to figure out a balance here. I'm just going to leave the learning rate as it is right now. I'm not going to make any change here. Okay. Entropy is basically referring to the degree of randomness you want in terms of the probability distribution, right? So I'm just going to leave that as it is. I think that is enough. I probably don't need this to be a lot more random. And then discount factor basically implies how much future rewards contribute to the expected cumulative, right? So for example, if you put in a discount factor of 0.9, right? So vehicle will include rewards from an order of 10 future steps to make a move. But then if you put in a discount factor of 0.999, like what you see on the screen here, right? The vehicle will consider rewards from an order of 1,000 future steps to make a move, right? So the way it decides what to do next based off, the point at which it decides to make a change in what it plans to do, it really depends on the discount factor. You can see how this is actually pretty critical. Okay, and then loss type. I won't go too much into that in this program. So, but when we provide you with the guides, feel free to go through the loss type. And lastly, we have the number of episodes between, or number of experiences between each training. All right. So this one basically controls how much experience the car should obtain between each model training iteration. As you're training the model, all right, you just want to decide, how much experience you should obtain between each before it goes on to the next one. Here, the recommended values are usually 10, 20, and 40. I will just go for 20 here. Okay, now those are all your hyperparameters. And lastly, your stop conditions. This is basically to decide how long you want to train this for. Okay, so I can set a maximum time if I want, or a short time. Now I'm going to set a maximum time here of 60 minutes. Now don't worry, we're not going to go through a full 60 minutes to see this complete. I will show you a sample of a completed training scenario. All right, so let's just go ahead and create the model. Okay, now what's happening is it's now provisioning for the training. It's going to take about 6 minutes. Again, we won't go through all those 6 minutes. I'm going to show you some different samples to show you both how training occurs somewhat, and also the evaluation piece, right? So let me just move on to another screen. Okay, now let's go ahead and click on this. All right, now this is an example of a training model. All right, now in here, as the model is being trained, right now there's no training occurring, but as the model is being trained, you can actually see the live video stream of the car going through the track, right? You can actually completely see that happening. Now, while that's going on, all this is actually being captured here. What is it capturing? Firstly, it's capturing the rewards that it's earning, and then it's capturing the percentage completion. Percentage completion is basically the whether it completed the race in terms of finishing the track itself. It's not tracking the time and stuff like that here, right? So the graph is not tracking the time. You'll get to see that under the evaluation piece. Right now, all the training for us, do you manage to complete inline rewards? Now, when you look at this graph here, for instance, you can, the way to look at it is this, right? Now, if you see your reward system working in a way that, every time your rewards get better, the completion rate is also getting better along with it, that typically means that your reward system is well tuned to making sure that it completes the track without any issues. Now, when you look at this graph here, for instance, now there's portions of it that seems to suggest this is great, right? So you can see here at this point here, right? So here is 70.5, and it's like the reward system also went up accordingly to give a pretty high completion rate. Now, but having said that, let's look at the best model that it predicted. Look at this line here that says the best model. And then you look at the rewards. The rewards here were not good. So that means in terms of the way the model was built, perhaps it's not perfectly tuned to get something that completes the track on time. Now, it may not necessarily be the case that the model that completes the track 100% is the fastest model. Sometimes there are elements of risk involved. You may want to say, you know what, I have a different way of doing this. That's fine. That's where the fun begins for you guys when you start creating models to take part in the competition. I'm going to leave that to you to figure out. Okay, so that's the whole training piece. Now let's look at the evaluation piece as well. Now the evaluation piece again looks like this. Once you start a new evaluation, again, it will show you a live simulation of it. For now, nothing is running, it's completed, so you do not see anything here. But you can see an example here, right? So here's what I mean. It's now sharing with you the time it took to complete and whether it completed the track itself. So you can see 100% completion, and then you see the lab completed here as well, right? And then there's one which says, look, there's only 13% completion, right? But the time is like, obviously the time is very little because it only completed 30% and it went off track. Okay, so this are all the ways you can do this. Now, just to show you how the evaluation takes place, let me go ahead and click on Start New Evaluation. Okay, now when you click Start a New Evaluation, again, you can choose the track. All right, so I'm going to choose the Solar Speedway simply because I had originally trained this particular model for the Solar Speedway. If you have trained a model for a particular track, it's always recommended to also evaluate it against the same track, right? So because typically you're going to find the results much better. I'm going to choose my racing type. I want to trial this for time trial and also the number of trials, right? I can say I only want you to do 3 runs, but Maybe I want to do a bit more. I can do 5 runs, right? And at the end, you can also say, I want to submit this straight away for some competitions we already have by default here, right? But in this case, we're not going to submit it for competition. We just want to evaluate it first. So I can just go ahead and say, okay, I've understood this. Let's start the evaluation. Okay, so the evaluation job will actually start, and you will actually start doing this. Now, once you're done with training and evaluation, you can still submit to the virtual race, right? So that falls under the right-hand section here. You see this option here that says submit to virtual race. You can actually do that. Now, for the ASEAN DeepRacer, or rather the AWS DeepRacer Women's League ASEAN, right? That one is going to be different. You will not be submitting to a virtual race. You'll actually train your model, you'll evaluate your model, and then once you're done with all of that, you're actually going to download the model and save it out, right? Once you've saved that out, on competition day, we'll be providing you with a special live environment platform where you will get to upload it and actually watch and tweak and control your cars during the actual competition itself. All right, with that, I am done with the demo, I believe. I'll be handing this back to Donnie. All yours, Donnie. Thank you.
Thank you, Suresh. What a wonderful demo. And for all of you, congratulations. At this point, you can build your own DeepRacer model and even tweak and tune your hyperparameters to get your best model performance. You're ready now to participate at AWS DeepRacer League. Here are a few things that you need to know about AWS DeepRacer League. Launched in March 2019, the AWS DeepRacer League had tens of thousands of developers race in person and online to see who takes home the championship cup. There are 2 ways to race. First is a physical race at AWS Summit, and the other one is to race on virtual circuit. Virtual circuit happens throughout the year, so watch out for new race release on the DeepRacer console. With Evo's new stereo cameras and LiDAR sensors, it enables 2 new racing formats in addition to time trial racing. In time trial racing, you will race against the clock in a single car on track race to see who gets the fastest lap. In object avoidance format, you will have a time trial race, but with the added challenge of navigating tricky objects on the track. And lastly, in head-to-head racing, you will race your model directly on the track against another model to see who crosses the finish line first. And for the virtual circuit, thousands of racers race in 8 virtual race months with time trial, object avoidance, and head-to-head division for a total of 24 chances to win. The virtual racing community is continuously pushing new boundaries, from hyperparameter tuning, reward function crafting, and all the way to creating their own virtual tracks. And don't forget, here are additional resources for you to learn more about AWS DeepRacer. And a big shout out to AWS DeepRacer Slack community, which you can join at join.deepracing.io. You'll find yourself a vibrant and helpful community if you want to learn with fellow developers across the world. Thank you for joining us in this session and had some fun together with AWS DeepRacer. Hopefully this session helps you to understand how reinforcement learning works and how to get started with AWS DeepRacer. Once again, thank you everyone. I'm Donnie and see you on the track.
All right. Now we're doing live Q&A session to answer some of your questions. So we have a list of really good questions and we want to address them all. And we're going to go in turn between Suresh and I to answer these questions. So let me read the first question. So the first question is, can you explain again what reinforcement learning is and how does it differ from machine learning? This is a really good question, as understanding reinforcement learning is crucial in AWS DeepRacer. So Suresh, do you want to take this question?
Yeah, sure, Donnie. So yeah, let me probably talk about it in this sense, right? So typically in the machine learning world, the 3 most common algorithms you would have, well, there's many, but I'm just going to bring it down to these 3 broad categories. There's supervised learning, there's unsupervised learning, and the third one, this is the one we're talking about here, is reinforcement learning, right? So supervised learning is something like this, right? So I'm going to give, say, a machine a set of images. Some of it contains cats, some of it contains dogs, and then I'm going to tell the machine that this particular image is a cat and this particular image is a dog, right? And over time, the machine actually relies on my feedback to actually figure out by itself when another image is actually submitted to automatically determine if that image is a cat or a dog, right? So that's supervised learning. Now, then let's talk about unsupervised learning. And that's the next slide, right? So unsupervised learning, what are you dealing with? You're going to actually just submit cat and dog images to the system. You're not going to tell the system anything, all right? It's just going to look at all these images, and by itself, it's going to figure out some patterns and decide, okay, it doesn't know that these are pictures of cats and dogs. All it's going to say is something like, hey, you know, all these images you see, I see a particular pattern. Let's call this cluster A. And then you'll pick up another set of images and say, let's call this cluster B. But it doesn't understand that these are cats and dogs. And when you look at those images that it clustered, you may find something interesting like, oh, check that out. The machine managed to actually figure out a pattern by itself without any input. It just knows that all these pictures here are dog pictures, but it doesn't know it's a dog. And likewise, it managed to figure out these are cat pictures, but it doesn't know it's a cat, right? So that's your unsupervised learning. Now, here's where it gets interesting. So you've seen these two different machine learning algos. Now, reinforcement learning, right, is slightly different from both of these two. Well, it's actually quite different from both of these two algorithms. It's based on a carrot and stick method, right? So it's like pretty much teaching a child, okay? So we're teaching a child, you said, okay, I'm going to reward you with a sweet, right? If you did something right. And then if you did not do something right, maybe, you know, I'll just put a slight pat on your hand or something to let you know that you're doing something wrong, right? It's a rewarding mechanism. Now, similarly, reinforcement learning machine algo works exactly in the same way, right? So it's actually attempting to learn a strategy that's optimizing an objective for an agent acting in an environment. Now, listen to what I just said. Don't these terms just sound familiar to what Donnie was just talking about a while ago, right? So this agent could be a robot, right? And the environment might be something like a maze. And the goal is to successfully, say, navigate the maze in the fastest possible time, right? And the reward system, how do you think it's going to be? Maybe my reward system will be every time you take a step forward, you are not hitting any obstacle, I'm going to give you a score of +1. But every time you take the next step and you hit in a block or you hit in the wrong, you know, as long as you face some kind of blockage or stop, I'm going to deduct points from you, right? So what does the agent try to do then to maximize its score? It's over time, it's starting to figure out, okay, if I go by a particular route without hitting anything immediately, I'm getting the highest possible maximum score. But every time I hit a block, I'm getting negative score. So clearly, I shouldn't take a particular path, right? So that's how reinforcement learning works. And reinforcement learning is so well suited for solving problems in like a lot of autonomous decisions. Speaking of which, Donnie, that brings me to the question then, which customer segments or industries are reinforcement learning applicable to in the first place?
Okay, thank you, Suresh. That's quite challenging. Okay, so reinforcement learning could be implemented in any kind of verticals, starting from telecommunication, financial services, manufacturing, or even e-commerce. And eventually, people will realize that they need to automate things and to make their system could auto-learn by itself. So it's really practical for any kind of industry. And there are two kind of industries that I personally think will be the first verticals to adopt reinforcement learning. They are banking or financial services and supply chains management. So for example, banking needs a way, right, to have a system that could give a set of recommendations that can learn by itself. For example, for risk management, they need to identify which activities or transactions are considered as a fraud. And for supply chain management, it's slightly more complex as there are many elements to be involved. And the bottom line is, if a system could predict and take action on how many inventory needs to be restocked to minimize the failure or delay on delivery, then it will be solved the basic challenge of supply chain management. And back to reinforcement learning is very well suited for solving large and complex problems because reinforcement learning models learn by a continuous process of receiving positive and negative rewards for every action taken by the agent. And it is really possible to train systems to make decisions under uncertainty and in dynamic environments. So that's for the second question. I'm going to read the third question. Suresh, are you ready?
Yep.
So this one for you. So what does slider means? What is a stereo cam, and how is it different from the usual?
Okay, yeah, good question. So, just to recap again, right? So, if you guys took note of the demo I was doing, and as well as Donnie who was talking about the cars, right? You would have seen us mentioning these two things. And one was LiDAR, and the other was stereo camera. And you would have also heard me mentioning these two interesting aspects. So I said this, right? I said I will use LiDAR sensors or stereo camera in a head-to-head racing or an obstacle avoidance kind of scenario. I don't really need it for time trial. So that tells you a little bit already about what kind of sensors this could be, right? So let's talk about LiDAR. Now, LiDAR is basically a sensor that's using like lasers. It will actually send like pulses of lights out, right? And then it measures the time it takes for the pulse to come back, right? So if it hits, imagine if there's an obstacle in front of it, right? So there's this 360 scan that's going on. It hits the object and reflects back. Based off the timing it takes for things to reflect back, right? You can figure out that there's likely to be an object in front of it, and as it has this vision inside it that looks like a 3D map, if you can put it that way. And then it actually picks up this set of objects here. Now, in a way, you have seen this kind of applications when you have seen a lot of today's maps, all that. So if you go to many mobile apps today, you see lots of mapping. You see 3D images of buildings that they don't have the picture of the building, but they can tell you that the building is probably like a little bit high and it's protruding out in a direction, right? A lot of that kind of work is actually done through the likes of LiDAR sensor, right? So that's in a way a LiDAR sensor, and that's actually provided in our DeepRacer vehicle, as in you have the option to add that on. Now, to aid the LiDAR sensor, we also have the stereo camera instead of the usual camera. Now, what's the difference between the stereo cam and the normal cam? The stereo cam actually has two or more lenses actually that can actually capture images with the same resolution and frequency. Then because it's capturing images from different angles and using double lens, it can actually determine the depth as well of the observed object. So imagine that value set that's collecting that kind of data, and then you map that against LiDAR. Your accuracy level becomes a lot more stronger in determining exactly what is in front of you from an obstacle perspective, or maybe which car is now right next to you in terms of a head-to-head race, right? Or to avoid crashing into another car. So in a nutshell, think of these two as sensors or mechanisms that actually helps you detect objects or things around you, right? So that would be it in a nutshell. Now, this is a great question, Donnie. I got a really tough one for you, right? So I know I was explaining this stuff to the students a while ago, right? So I was walking through all those hyperparameters, but I was just showing them some example. But the top question I kept seeing is a lot of students were actually asking me this: what's actually the best hyperparameter configuration they should actually put in? Is there a best hyperparameter configuration in the first place?
Okay, yeah. Okay, so to answer this, I'm going to explain a bit about hyperparameters in machine learning and also in reinforcement learning. So hyperparameters is one component in machine learning and reinforcement learning. So to give you a full spectrum of answer to this question, we also need to consider reward function and action spaces. The essential thing about reinforcement learning is to have your model to converge between exploitation and exploration. And this is pretty much understandable when you look into the graph during the training and evaluation. So the easy way to see it is if you see the completion rate is 100% and the reward function find its peak, then you know that your model has converged. And that's a really good thing. And you have plenty of variables to experiment with. If you go into the DeepRacer page, there's a variable list which you can also find waypoints variable, and you can use the variable to calculate direction of the vehicle, as well as considering to adjust the throttle to make it faster or slower. So our first advice is to look into the variables and use what you need. And okay, so we also have a few questions regarding batch size, epochs, and also the learning rate. So let me share a bit about this. In reinforcement learning and AWS DeepRacer, you also need to tweak your hyperparameters. And the thing about hyperparameters is it correlates one to another. And back to the question regarding the epochs, what's the ideal number? And you might hear quite often about epochs, batch size, gradient descent or ascent or learning rate. So let us explain this a bit. In machine learning, we are dealing with a big data and we cannot pass all the data to the machine. So to overcome this problem, we need to divide the data into smaller sizes. Therefore, we have experience buffer and batch size. And we are doing sampling to update the weights of the neural networks at the end of every iteration, and that's the epochs. And for epochs, it's highly correlated to the number of batch size, as the training data corresponds to random samplings from the experience buffer. Right. So for gradient batch size, the available options are 32, 64, 128, 256, and 512. And for the epochs, the available options are ranging from 3 to 10. And as Suresh mentioned, that you might want to use a larger number of epochs to promote more stable updates, but expect a slower training. But when you have the batch size is small, you can use a smaller number of epochs. So there's no definitive answers, and the best way to answer this kind of question is based on your experience doing trial and error. And we mentioned that hyperparameters is highly correlates. Like for example, if you want your model to learn faster, you need to adjust the batch gradient size, number of epochs, discount factor, and also action spaces. If you want your model to be more robust, in the sense that it could race in any other tracks, you need to adjust the batch gradient, entropy, learning rate, and also action spaces. And you need to jump into the code and see it for yourself. If you just get started, it's advisable to leave everything by default and you can focus on your reward function. And to answer one question, is Python mandatory? And I could say that yes, in AWS DeepRacer, we use Python 3 to craft your reward function. And last but not least, and I think this is our key learning on DeepRacer, is be patient. You don't need to build a very complex reward function at first. Start simple, start small with your reward function, and then over time, you can add more features one by one into your reward function. And this will make it easy for you to understand the dynamics and observe your data points. Okay, so I think we've answered all the questions, Suresh. So over to you, Suresh.
Okay, thanks, Donnie. So, so with that, we have pretty much wrapped up this session. So we thank you all for your time today. Now, before you leave, do remember to complete the survey as you are exiting. This will help inform us of newer topics that we could deliver in our next few sessions coming in the next few months as well. Right, and also do not forget, if especially you are from the ASEAN region, right, and you are a woman contestant, so take note of the AWS DeepRacer Women's League. It's a really unique experience. No one has had this opportunity. It's pretty much a world first scenario where you're going to get to take part in a real life race virtually as opposed to doing it physically, right? So that's pretty much about it. So thank you, everyone. Look forward to seeing you all at the next webinar that we have.